So we are working for free for Amazon, I'm afraid. Right? So he's able to, by using our special rule induction algorithm, he's able to find this kind of rules. So they are supposed to be very novel, very interesting rules. I have no idea. But how do I know? He used warning in order to measure the novelty of the pattern. So, and the pattern here is composed of an antecedent and a consequent, A and B. So what would you expect about A and B in order for the relation between A and B to be novel? For instance, that I never think any connection between A and B. That's the first thought. And the other way to do it is to think of, well, there is a connection between A and B, but actually a very, very, very weak connection. So I would bet that the connection between C and Taylor, right, is a short distance connection. If this is a short distance connection, this means that probably represents a fact that I already know. So I'm looking for a connection with a long distance. And how this method deals with that, the method uses warnings as a tree in order to find the concept of A, the antecedent, the concept of B, and then try to compute the distance. So, conclusion is, the longer the distance, the most interesting the pattern could be. Right? And the second good thing with that is that he was able to do this automatically. Right? So, how he measured this? Well, he computed the distance between these two concepts, one in the antecedent, the second one in the consequent. And he measured the distance between two concepts, which is given by the path, which connect two concepts in one. That is the first problem. The method assumes that the concept that you extract from the document are already on the ontology. What about if you find a word which actually is not in the ontology? What the method does is to assume that there is a very, very long distance, because like doesn't exist. But very, very, very long distance for the method at the same time means that, oh, it's very interesting. So that's one of the problems, that you have to rely on the fact that every concept involved in every rule has to be in ontology. Otherwise it's impossible, right? I mean, the result is very bad. So one point is the distance, right? And the other points are we're talking about this ontology warning, which actually is a tree of concept with some very specific semantic relationship, right? The thing is that should matter whether you move horizontally or vertically. If you move horizontally, this means several things. For instance, you are dealing with some antonym. So antonym, for instance, should be stronger, should be more interesting, because the connection is quite long. But the bad thing that could happen is that Ci and Cj are synonymous, because most of the time that relationship is not going to be very novel, so you can discard it, right? So how this method deal with this computation? Just I'm not going into detail how this guy came out with this information, but every relationship, actually this is the kind of relation that you may find in Warner. They are predefined. Yeah, you cannot add more relationship. You can add more concept, but no more relationship, right? And every relationship has a direction. This guy has established some sort of weight. So, for instance, the longer the weight, the most interesting is the connection. If you look at the example, the table shows that the best one to be an antonym. But obviously, you are moving from one concept to other concept, which actually know our neighbor. So So actually what you are doing is to try to add up, right? All the path you are crossing, and all the kind of direction that you are moving, right? If you move down, you move up, it's totally different. The good thing with this is that this guy tried this method of knowledge discovery from text with human. What they did actually is to rank the evaluation of each pattern by the method, and they use human evaluator, and they compare and they compute some sort of correlation. And this was the correlation. Actually, not bad, but actually it's not so perfect. So at least they got a positive correlation. That means that there is some fair correlation between what the system says, which is about a novelty of a pattern, and what the humans say about the novelty of a pattern, right? Right. But we have several problems with this. One of the problems is that, as I said before, this method is highly dependent on our external resources. So if you don't have WordNet or something like that, there's no way to do anything, right? Every computation is assuming that you can go through this kind of ontology, whether it is WordNet or not, but you have to provide an ontology. So what about if you don't have you have a practical problem in real life application? That if you move to one domain, like for instance history, for instance finance, or so on, probably you won't find some particular ontology for that domain. So you would like to have a method which works, hopefully, independent of any external resource as long as possible, right? So the other method that was developed was exactly considering this kind of constraint. First of all, this method assumed that, okay, you can do a little more with the text. So as you can see with Mooney approach, he used some words, he used some very basic relationship, but he's not using the whole potential of the text. That's the first thing. The other thing is that you are too dependent on the external resources. So, and the other thing that Mooney's approach is not able to do is that not the hidden pattern, the pattern that you can find, not the pattern that you can instantiate, which is different with the same. There you have a problem of ambiguity. Different people use the same word for different things. Here we are talking about the pattern that you can find from the data mining point of view. So in most of the hidden patterns, which are actually never are the result or the product of crossing a lot of information, which is not the case in most of the text mining techniques that we have seen. So what a new method did is try to make good use of this element and try to provide a new way to uncover patterns from data. So in order to understand the method, let's think about the following. Let's suppose that you have a bunch of documents. The document could be abstract or in a technical domain. So what you usually do when you are getting started in a domain or in a research problem, you start reading some part of the abstract in order to make a general idea what the abstract is about. Then you read the next abstract, you read the next and the next and the next, and then once you have understood something of the abstract, you try to correlate stuff. Obviously, you can come out with very interesting things. So what the method proposes is exactly to do that kind of thing with using evolutionary computation method. I'm not going into detail, but actually I would like to I would like to show a general view of the model. Actually, what you got at the beginning is a bunch of documents. You have, for instance, abstract of a certain domain. Actually, in the model that I'm talking about, the abstract are in the domain of agriculture, agronomy, this kind of stuff, but to be possible for any other domain, right? You can see here, there's no going with something of an ontology or something like that. So the only input for the model is a set of documents, a corpus of documents in one particular domain. Right, so you have the document, you have some information extraction task. So we assume that, okay, we have natural language text, but not all the information from the text is useful. So what we did is to extract partial information from the text, and we build, as Moody's approach, we build rules. And once we have this rule, from the document, we also can extract all the kind of information. For instance, we can get all the kind of information like semantic information.